In this second part of the compression unit, we'll look at compressing using methods that exploit how text is repetitive in a different way, not just single characters being more frequent than others. And let me start with a maybe not super serious example why this makes sense. If you have a text like this, of course it's English text, so it will have something like the character frequencies that we've seen in the Huffman chapter, and they're not completely uniform, so you can compress it a little bit. But if you make that text much longer, and in The Shining he does, it feels like this should be compressible much more. But if you just take the character frequencies and you double the length of the text, you still double the length of the coded text, even if it's completely predictable, like in this case. And that feels a bit wasteful. So anything that works character by character and looks only at how frequent specific characters are will not be able to capture such repetitions. And so that's an intrinsic limitation of character codes if you only look at single characters. So what can we do? I guess obviously we have to encode more than one character, if that's an inherent weakness of character codes. So the term that people use for this in the context of compression is a phrase. That's a substring of the source text that's represented by a single code word. And the hope with that is that we can somehow capture these kind of repetitions where Huffman couldn't do that. Before we come to methods that do that more effectively, we'll look at something that seems very limited, but is a good stepping stone and also a building block. I mentioned this several times. Maybe it's a good point to take a step away from concrete topics and mention this. Many compression methods, especially the ones used in practice, are not one single textbook method. They combine different things, and they often use them one after the other. So they apply some pre-processing and then another step, and then maybe at the end they do some Huffman code. Or they have some phase of run length encoding that we'll cover next in it. Many of the methods are in isolation not as strong, but they can be combined. We'll come back to that idea at the very end. But for now, I want to start with a first type of compression method that's very simple, but still shows you how powerful exploiting repetitions can be in the extreme case. It's a simple one. Okay, so what's the simplest form of repetition we could have in our source text? Just words that consist of the same character repeated over and over. And we call those runs here. That's where the name comes from. Not to be confused with runs in the context of sorting, where this was a subword of the input, contiguous segment that's already in order. That's not what this stands for here. It's just several times the same character. You can easily imagine how you can obtain something like that if you have an image that's just monochrome, just two colors, say a simple scanner that only does black-white. Then maybe if you have a high-resolution image, you will have many of these runs. So that's one application where this naturally arises. We'll simplify our life here and look basically at binary alphabets only. But much of what run length encoding does can be generalized to arbitrary source alphabets. The binary alphabet has one nice additional feature that we'll come back to that makes this a bit cleaner, but it can be extended. The basic idea of a run length code is to split the input into phrases that are just runs. So if my source text is this, I'll decide I'll have these three phrases, and I can say this is 5 times a 0, that's 3 times a 1, and that's 4 times a 0. Even just writing it out like this, if you imagine these are a bit bigger, of course that's much more concise to write the length instead of repeating 0 so many times. So if you look at this a bit more closely, what do we need to store to reconstruct a source text that we have split into phrases like this? Well, we somehow need to know what the first bit of S was. So we store 1 bit for the first bit of S. And then all we need for the rest is the length of the subsequent runs. Because by definition, I never have a run of zeros followed by another run of zeros. That's useless. I can just make that one run bigger. So I can always alternate between 0 and 1. So we don't really have to store the character that is repeated because there's only one other choice. That's what I said earlier, where binary is nice. If you had one run of zeros, it will be followed by ones. For general alphabets, you would have to store the new character on top of that. That's the only change. So our example from before would then be 0, because we start with a 0 bit. And then the lengths of the runs are 5, 3, and 4. And that's enough to reconstruct that source text. So that's basically all. But we've cheated so far. I've just used this list of numbers, and I used a comma and all that to kind of separate where one number starts and where the next one stops, or where one number stops and where the next one starts. We'd really like to encode this with few bits, so reserving something like a comma character and so on is not really what we want. And so we have to somehow deal with the fact that these numbers can be arbitrarily large. We don't know upfront how big the run is. And still, we want to not have a separate character like a comma that separates it. So we would like to have, more specifically, the goal would be to have the coded alphabet as binary as well. And if that's my restriction, the question becomes, how can I store arbitrarily large integers if I just have these 2 characters, right? And to work up to that, let's collect a bit ideas, because I don't know if you ever thought about this. The question here is asked in a slightly more general form, not just for numbers, but you have this same question for any kind of strings. If you have a programming language like Python, you can write down strings, and there's no limit on how big they are. I mean, there's a limit practically on how big your memory is, blah, 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 but not conceptually. How does Python do that? How does Python know when one string stops and when the next one starts? I'll just leave it open. Okay, many people aren't sure. It's something you don't think about it unless you have some low-level programming course. You're not forced to think about it. But it's obvious, right? This is a problem that somehow someone who implements a programming language, they have to solve that problem. You need to know when a string stops, right? It's quite obvious. How would you do it? Okay, no, I didn't follow some of the answers. Yeah. Okay, it's too fast. Can I zoom out? Helps a little bit. I love run length encoding, but we haven't covered that yet. Okay, I think I've seen the 2 main solutions scroll by. I haven't pointed them out, so I don't know if you spotted them. There's basically two options. Okay, if you want an arbitrarily long string, you can either, before the string starts, write down how long it is, and then you have so and so many characters following. That's a convention. I think Pascal, this old, I don't know if do people still know Pascal? Nobody's using that anymore. It's a programming language that fell a bit out of fashion. But I think Pascal used this convention. Do people know Delphi? That's something that was still a little bit in use when I started programming. That's based on it, but I think that's it fell also. This solution with prefixing the string with a number for the length is also not the most common solution. The other solution is having null terminated strings. So you do receive a special character even in ASCII. The all 0 bits is the universal sign of end of string. It's a kind of convention. It's not enforced, but C and C++, Java, I think they all use that kind of convention. I'll take it back for Java. I think Java is essentially an array which stores its length. So maybe Java also does the Pascal convention. Oh, I have to look this up. Okay. Basically 2 options, and I won't comment further on which ones are more common. You can either store the length before you start, then the characters, or you store after all the characters a special character that tells you that's the end of string. Okay. Okay, thanks for playing along. Maybe I can collate the answers a bit. Okay, it tried its best to collate. That didn't work so well. They have to polish their AI more. Maybe some of you should go and work for Slido. Okay, more seriously going back, 2 options. Maybe should write down what they are. One option is start with the length, then as many characters. Option 2, I just call it null terminated strings. That's the terminology that C uses. And so you write this as \0, the 0 character. Okay, maybe now you remember. Maybe you have encountered this. But in a high-level programming language, it's so convenient that you don't have to worry about it, that you ignore it. Now, I don't know if you caught me on this, but option 1 is still cheating. If the length of the strings can be arbitrary, how do I store the length of the string? That's kind of the same problem we started with, right? All right. So what we really need, especially for run length encoding, is a prefix-free code, something that's decodable unambiguously, or all of the integers, arbitrarily big. Is that even possible for an infinitely big set? Maybe another question when you first see it, you wonder, can you do this at all? But obviously, yes, because we can just use unary encoding. We write as many zeros as the number is that we want to represent and follow it by a 1. Right? That obviously works. It also obviously is not that great. It's very long and wastes a lot of space. Even for 30, this becomes really big. So we don't want to do that, but it's a theoretical possibility. What we like much better is writing numbers in binary. Right? The standard binary representation or the decimal representation is essentially a same kind of trade-off. That is fine if only we knew how many digits the number has. So that alone is way too long. And the simple trick is combine those 2 things. Use a binary representation for the number, but prefix it with the unary representation of how long that binary representation will be. That's pretty slick, right? So we store the length of the binary representation in this kind of code. And then we append the normal binary representation of the number. So the numbers will be twice as long, roughly, as they would have been if we just store the binary bits. But that wouldn't be a prefix-free code. We wouldn't have known when to stop, whereas now we do. And that's called the alias gamma code, because you can play the game further, but we don't need that. It's basically these 2 ideas, but if you look at it closely, you can shave off 1 bit or 2. all the numbers that we represent are positive. So they will always have length at least 1. So we can store the length -1 instead, and sometimes save a bit from that. And also, if you combine these two things, the binary representation of any number starts with a 1 if you restrict it to the meaningful digits. So we don't need to store that 1, or expressing the same thing in a different way, we can omit the terminal 1 of this unary representation, because we know the binary representation will start with a 1 anyways. And so what comes out of that is this encoding, and that's something, okay, we'll practice it in an example in a second. So again, what is it? The length of the binary representation, -1, that we write in unary, and then followed by the binary representation. So let's do the example of 5, okay? What's 5 in binary? Well, it's 101 because it's 4 and 1, okay? Everyone awake? The length of that is 3, so L is 3. L minus 1 is 2, so I'll just stick 2 zeros in front, and that's the gamma code. All right. Let's practice that a little bit. To make it not too easy for you guys, this is a longer stream of bits, and I just want you to decode the first number that's encoded in Elias gamma code in that stream. So you'll have to figure out when to stop. That's my point. Okay? Yep. So you have the bit string on Slido, which means I can go back and show you the instructions instead. I've seen the right answer come in. I've seen other answers come in too. Still a good bit away from the 100 that sent the attendance code, okay? So let's leave it a little bit. Oh my God, some of you really think I'm cruel, like the big numbers you send. That'd be really, really, really mean. Let's get to 70 at least, and then I'll show you what you sent. Okay, there we go. Lots of numbers. And the free text polls can't do correct answers, but Let's do it together very briefly. I haven't really told you how to decode. I only showed you how to encode, and you had to figure out for yourself, right, how to invert that. Remember, the first is a run of zeros that tells you how long the binary representation is, but that's the length, so it's 3 zeros, but the length is 1 more. So you have to take the next 4 bits and decode that in binary. That's 1 and 4 and 8. That's 13. Okay. And yeah, many sent that. And then he continues with more stuff. So also notice that this kind of code is surjective, is onto. So you can any kind of bit string has a meaningful decoding as a sequence of integers. You can always take random bits and practice this if you want. You will usually get small numbers, but that's what it is. Okay. Here are a few systematic examples, again, just to practice the whole run length encoding. So run length encoding, again, it uses this gamma code to store the length of runs. Let's do the full run length encoding on 2 examples. First, for encoding, remember the first thing we store is just the first bit, because we need to know what we start with. So that's the 1. Then we find the length of the first run, that's 7 ones. And we encode that in gamma code. Again, I'm doing just only one more. 7 is 111. That's a binary representation of length 3. So I put 1 less 0 in front, 2 zeros. That's my gamma code. The next run has 2 zeros, but I don't have to store the 0, just that the length is 2. And in gamma code, that's that. Then we have a single 1. The gamma code of 1 is just 1. That's convenient. Doesn't make it longer, for example. Then we have a very long run, decodes to this. And finally, a run of length 11 encodes to that. You can go through those in detail and double check the calculations if you want, then you can practice it. But that's what happens. Now, just visually, you see that we made the string shorter, right? If there are substantial runs like this, then run length encoding is effective. Let's practice decoding as well. It's the same game. We first find the first bit. That will give us the character that we start with. So it's a 0. Then we find, after this first bit, excluding this first bit, the length of the first run. It has 3 zeros. That means we read 4 bits to get the binary representation of the run length. That's 13. So we start by outputting 13 zeros. And then we keep going. Next number is 2 zeros, so we read 3 bits as a binary representation. And that's the number 4, so we produce 4 ones. I guess now you get the hang of it. So after this, there's no zeros. So we just read 1 bit, and that's a 1. So we append a single 0 at the end here. And then we have one more number. We read 1 0, so we read 2 bits for the next binary number. Oops. And that's a 2, so we append 2 more 1s at the end of this. I hope the process is clear. If you practice it a few more times, it's actually fairly easy to do. Taking aside that you have to compute the binary representations. As I said earlier, you can extend the same procedure to larger alphabets. Conceptually, it's the same thing. You just have to store the character that you repeat as well. So you need a character code alongside this. But we'll usually only use the binary version here. It's in use in direct form in some old formats for scanned images where essentially you had monochrome images, but at higher resolutions. It's a little less used in isolation now, but it will come up later as part of a bigger pipeline. What do we like about it? It's simple and fast. Because of its simplicity, it's fast to it can be implemented to be very fast. And it can do something that the methods that we've covered so far could never do. Namely, it can compress something that has n bits down to essentially a logarithmic number of bits, if that input is just all zeros, for example. Right? It's one long run, and then you store the length of the run instead of the actual many bits. So the best case for compression here is extremely good. Huffman would never achieve something like this. It's only or depending on how big the alphabet is, it can be a super constant reduction, but it won't go down to log n. Now, of course, the negative is it's a very simple scheme. It only picks up exact runs, and you hardly ever have those. In particular, you don't have any compression unless the runs are of length at least 6. You can work this out by comparing the numbers, the length of the runs, and the representation of the number in gamma code. And there's 2 cases, interestingly just 2. For lengths 2 and lengths 6, writing the gamma code is longer than spelling out the run. For all the others, it's doing no worse. But remember the no free lunch theorem? We have to have something like this. We cannot always compress. The best thing we could do is never make it worse by leaving it as it was. But you can never achieve strictly better sometimes and never worse. That's impossible. So we have to have something like this. And it's just 2 numbers, so it looks pretty good. But it can mean that run length compression makes the input longer if you have these kind of run lengths.